Just a quick look at what we were doing yesterday, and we have a few problems in the worksheet we need to take care of. So we were mostly doing cylindrical coordinates. I know the projector is kind of blocking the view for people online. So cylindrical coordinates, it's just the polar coordinates plus the z-axis dimension. So that is nothing really new there, except that you are having the height added to the surface area. Okay. Spherical coordinates was a little bit more unfamiliar in terms of what exactly it is coming up with. It's got distance and two angles instead of having two distances and one angle for the cylindrical coordinates. Okay. In particular, this angle here, this is the one to get used to. It starts from the North Pole and kind of sweeps through into the South Pole clockwise, and it stops there. Okay. And again, the reason is that every time you're at an angle of phi, you are able to go around and come back to that same place. So the upper limit here is not 2 pi, it is pi. This is the same as what you had for the polar coordinates or the cylindrical coordinates, nothing new there. Rho is a radius, that is not the same as r. The conversion is r equal to rho sine phi, and the height z in cylindrical coordinates would be rho cosine phi. Okay. Those are the two things that will help us convert from cylindrical to spherical coordinates. So this is your r cosine theta, this is r sine theta, and z is from here. Of course, if you square and add those terms, you will get the square of the radius, which is just Pythagoras theorem. And I think the mysterious part, the price you have to pay from going from one coordinate system to the other is a more complicated dv each time. Okay. Rectangular coordinates, it was easy, it was just dx dy dz. And that was easy to visualize because it's just a box, right? dy dx dz. Things started curving around, and that's when things became slightly more complicated here. Okay, it's not dz dr d theta, it's dz r dr d theta because of this curved side here. But in this case, your dz was not too bad. Sorry for my bad drawings. So the dz here is the height, and the r dr d theta is still from the polar coordinates on r2. In spherical coordinates, it's a little bit more complicated because your increment in radius is d rho, and your r d theta is rho sine phi d theta. That's why there's a sine phi in there. Okay. And you have rho, that's radius, increment in radius. So this rho and this rho multiplies, giving the rho square. And of course, your d theta is here, and d phi is the small angle in phi. So even if that looks kind of complicated, there is a reason for each of those terms coming up there. And as you saw in the examples yesterday, it kind of makes our life easy if you have a spherical geometry in the problem. Okay. One of the slightly unexpected things that you kind of see in the spherical coordinates problem is, if you see a cone, okay, you may not think that it's something that the spherical coordinates will take care of easily, but then you can, if you think about its 3 dimensions, and if you just carve a part out of this like this, okay, what you're really getting is a cone that you're lifting out of that sphere. So if you just insert something and just carve it through into the center, okay, you're really getting a conical shape. Though if you're looking from there, it looks like it's a straight line. It's not. Okay. It kind of curves around, and that's why a cone is nicely represented by this angle in the spherical coordinates. So in general, the angle phi equal to any number, okay, between 0 to pi, use a cone in R3. Of course, some of those cones might look a little awkward because if phi is pi over 2, it kind of looks like a semicircle. Okay, so when you say a cone, you have to take it with a pinch of salt there, right? So this is phi equal to 0, okay. And for all these values here, okay, that is going to be a cone. Right? Any value here or here, that's a cone. If it hits pi over 2, then it becomes a hemisphere. Okay, so that is kind of an exception. And again, you can go down and that will become a cone like this. Then you have swept through this much angle here, okay, because you're starting from the North Pole and you're going down. We don't usually talk about cones here because it's just computationally not very relevant. That's why we always keep the cones above the XY plane, but doesn't mean that they're not possible. Okay. So whenever you see phi equal to some angle, that represents a cone in spherical coordinates. And that's really useful when you're doing some of these problems, especially with the ice cream cone kind of situations. Okay, so some of the more other famous cones. So this was the first one. Okay. Phi equal to pi over 4, where the cone is kind of equally inclined to both the axes there. Okay. What if you had z equal to square root of 3 times the square root of x squared plus y squared? When I say famous, that means the angles are something that we are familiar with. Okay, that is what famous means, not famous like in a celebrity status. So again, make use of your conversion. So you have rho cosine phi equal to square root of 3 times, this is r, which is rho sine phi. So tangent of phi equal to square root of 3, and phi would be pi over 3. Good. And there is one more famous cone. That is, if the square root of 3 is on the left hand side, z times the square root of 3 equal to, it's all about changing the steepness of the cone. Okay, the cone is either kind of closer to the z-axis or it is away from the z-axis. Okay. In this case, you have rho cosine square root of 3 times rho cosine phi equal to rho sine phi. Keep those things right next to you when you're doing a problem so that you can convert it both ways. Okay. And you get tangent of phi equal to 1 over square root of 3. So phi would be pi over 6, so 30 degrees. Those are the 3 famous cones. Okay. What if you had z equal to 5 times the square root of x squared plus y squared? That is some random cone. I don't know what that is. Okay. These are the ones that you can easily pull out your angles for, and this kind of looks nice because those are 30 degrees, 45 degrees, and 60 degrees from the z-axis. Okay. So I know the radian measure is a little bit cryptic, so this is 45 degrees from the positive z-axis. This is 60 degrees from the positive z-axis. And that's 30 degrees from the positive z-axis. And it's a plus z, that is the axis. Yeah. All these measurements are done clockwise from the North Pole. So this is the closest to the North Pole, right? 30 degrees first, 45 degrees next, and 60 degrees last. Okay. So the good thing is, if you see any of these cones, and if you're using spherical coordinates, just use these without going through all the process. Okay. That is why I'm writing this down. So make a good note of it somewhere, keep it next to you. You never know, right? So if a problem says you have a cone inside a sphere or 2 cones inside a sphere, you can make use of these phi values without going through all these derivations over and over. That's how you save time. Because I've always seen students who, every time they get x squared plus y squared plus z squared, they try to derive it from scratch from all that stuff. On a test when there is no time, they start from that, and then then they make a mistake, then they have to correct it. So just if you write these, you can just make use of it without proving it over and over. Okay? That's one of the reasons why I encourage you to come to lectures and kind of pay attention to what I tell you about these things. All right, so any questions about anything? I know there's a lot of things written there. Any questions about any of these before we dive into the next few problems in that worksheet? All right, so now that we have all the cones in our control, let's look at problem number. Oh, by the way, I have the answers to all these questions on Canvas, so I won't be doing any of the integrals in detail in the lecture. So just do it yourself, compare your answers. Okay, I'll just be doing setup during the lecture, so just to save some time. All right, so let's look at problem number 5. Actually, this is a problem from the textbook, I think. It's problem number 36 in section 3.6, I think. All right, so problem number 5 is to find the volume of this following thing in the first octant. Okay. Worksheet number 10. And first octant is first quadrant plus the upper half plane. Okay. There are 2 cones, so one was not bad enough. Z equal to square root of x squared plus y squared, and z equal to square root of 3. As I said, these are the ones you can easily pull out the values for. And it's inside the sphere of radius 1. All of you should understand this as the square of the radius. Okay, there shouldn't be any doubt or confusion about that term. That is the square of the radius with the sphere centered at the origin. All right, so the picture is a little clumsy. I mean, if it's a sphere with kind of 2 cones carving it through. Okay. So your main task is to figure out which one is closer to the this is the positive z-axis. Okay. And don't forget your phi is going in this direction, so you should hit the first cone first, second cone second, like this. Okay. And that's where you have to make use of all those things I wrote earlier. So one of them is the first one, one of the second one. Okay. Meanwhile, this should help you with the radius. So 0 less than or equal to rho less than or equal to 1. Whenever you see the first octant, don't forget that you're also in the first quadrant in the xy plane. Okay. So theta, that is probably the only place where theta is going to change. So usually it is between 0 to 2 pi, but when you're in the first octant, first quadrant, 0 to pi over 2. So read the question, don't just put 0 to 2 pi. What do you think would be the limits for phi here? So this is cone number 2. So which cone is closer and which one is farther from the z-axis? 45 should be closer. Okay. So this is z equal to the square root of x squared plus y squared, which is phi equal to pi over 4. And this is the less steeper one. Okay, so it's z equal to square root of 3 times the square root of x squared plus y squared. And that is phi equal to pi over 3. Again, that looks bigger, but you're measuring from the positive z-axis. Okay, so 45 is hit first, 60 is hit second. Okay. In no circumstances should we be writing a smaller number here and a big number here. Okay. That is obvious. So No matter how we look at it, 45 is less than 60. All right, so the setup for the volume would be the triple integral of 1 dv. And it doesn't matter which one you write first because all these limits are numbers. Okay. So since we are using the right coordinate system, that saves a lot of headache for us. So it's rho between 0 to 1, phi between pi over 4 and pi over 3, theta between 0 and pi over 2, 1. Oh, it's what did I write? dz, no. 1 rho square sine phi d rho d phi d theta. And then you can separate it, do it at your own convenience. Okay. Again, the answer is on canvas, so please do this yourself. Make sure that you are comfortable with the integration. Okay. Do I have the wrong answer there? I have to check that. Pi over 3 is 60 degrees, tangent of 60 degrees is square root of 3, yes. Square root. I think I used pi over 6 in my solution. I'll correct that. Okay, sorry about that. So. All right, I hope this one makes sense. 60 degrees is after 45, yeah. All right, any questions about the setup? Is this the right question I'm doing, or did I change the question between? Sometimes I flip things around just to make a variety of questions. So let me just worksheet 10. Yep, same problem. All right, see, I'll fix that after the lecture. Okay, maybe an hour after the lecture, and I'll upload a corrected file. All right, let's do the next one, which I kind of borrowed from the textbook with different numbers. Do you have the question? Number 6. Find the volume which is inside the sphere and inside the cylinder. Okay, read the question carefully. It's both inside cylinder, which is x squared plus y squared equal to 4, and inside the sphere, x squared plus y squared plus z squared equal to 9. This is probably the first instance where you have to make a decision about, is it better to use cylindrical coordinates or spherical coordinates? Comes with experience. The first time this question is thrown out there, it's not easy to answer it one way or the other. You have a cylinder and a sphere, right? So So far, you have been told that cylindrical coordinates is for cylinder, spherical coordinates is for sphere. So what if they come together? Which is, since using both is not a good idea. Okay. You should stick only to one. So what do you think would be the better of the two evils? So the usual rule of thumb, okay, this is not 90, this is probably 99% true. The usual rule of thumb is that it's easier to do cylindrical coordinates for sphere than the other way. Okay. It's very difficult to convert spherical coordinates to cylindrical coordinates because of the way a cylinder is, there are flat sides. Okay. And spherical coordinates is built exactly out of something that is completely spherical. So it's very difficult to go from spherical coordinates to cylindrical coordinates. It's much easier to do the other way. Okay. So cylindrical to sphere than spherical to cylindrical. So in other words, if you have a situation where you have a cylinder and a sphere, always use cylindrical coordinates. Okay. Now, is that always the case? I want to say yes, unless there is something in the problem that says, it's not a good idea to use cylindrical coordinates. Okay. But most of the cases, if you have a cylinder in the problem, use cylindrical coordinates. Okay. So in this case, you are not finding the volume of a cylinder. That you could do. Okay. The problem here is that the cylinder is sitting inside a sphere, and the sphere is kind of covering it up. Okay. So there is a cap here. Okay. So let me redraw this picture. So this is your cylindrical part. There is a cap that is created by this spherical thing, both at the top and the bottom part of the solid. Otherwise, you just need to do pi r square h. Okay. There's no complication to this if it was to just find the volume of a cylinder. The cylinder is sitting inside a sphere. So this is x square plus y square equal to 4. That is a cylinder. And the sphere is kind of keeping it closed. Okay. That is the lid at the top, and that is the base at the bottom. So the base is curved, the roof is curved, and those curves are created by the sphere of radius 3. Okay. So if you write this as z square equal to 9 minus x square minus y square, you have z equal to plus or minus the square root of 9 minus x square minus y square. The positive root is the upper hemisphere. The negative root is the lower hemisphere. Okay, that's the one. Those are the two parts that are kind of covering it up. Okay. So this is z equal to square root of 9 minus x square minus y square. And this is z equal to negative square root of 9 minus x square minus y square. So if somebody is asking you what's the height of the cylinder, it keeps changing, because if you stand here, okay, that height is different from what you feel if you stand here, because it's a curved base and it's also a curved roof. All right, so the z limits would go from the base to the roof, or the floor to the roof. Okay, so it's negative 9 square root of 9 minus x square minus y square less than or equal to z less than or equal to square root of 9 minus x square minus y square. But since we have decided to use cylindrical coordinates, that's the same as writing negative square root of 9 minus r square less than or equal to z less than or equal to square root of 9 minus r square. Floor to roof. And I know it's very tempting. You have a square root and bunch of squares sitting in there. This is not 3 minus r. Okay. So don't don't do those kinds of mistakes on calculus 3 exams. And if it was 10, it's probably less tempting. 9 is kind of pulling you there. Now, what do you think would be the limits for r and theta is? Because we are using cylindrical coordinates, that's z. What about r and theta? Yep. R is between 0 and 2. That's because the radius of the cylinder is 2 based on this equation here. Okay. What about theta? So 2 pi. So the only complication here is to figure out the height, which is created by these hemispheres at the top and bottom. Okay. So the sphere has to be bigger than the cylinder here, otherwise the problem is not sensible to do. Okay. All right, so the setup, and I'm hoping that this time my solution is correct. Would be, well, don't forget you have to write the r limits first, or the ones in terms of r. Okay. Square root of negative square root of 9 minus r square to square root of 9 minus r square 1 dz. The other ones we don't care which one you write first or second. 0 to 2, 0 to 2 pi r dr d theta. And once again, this r is going to help you with the integral part. Yeah. Yes, it is. Otherwise, it won't create this roof and base as we are thinking it is. It has to. So it has to look like this. You know, there's a hemispherical cap and there is a hemispherical base, and the cylinder is sitting like this. Yeah. All right, so let me just make sure that my solution is correct there. Worksheet 10 answers, number 5. Yes, that one looks right. Relief. Okay. That was number 6, right? Yep. All right, number 7 is the highlight problem. Okay, this was asked in that same final exam which had the polar coordinates question which I did last week. A lot of students had difficulty with this question. Okay. And that's one of the reasons why I do it every semester, just to make sure that you make right choices when you get these questions. So. Number 7, yeah, the last question in this worksheet. I hope I didn't skip anything, right? Okay. So number 7. The problem is this: there is a sphere and there is a plane. Okay, so the sphere is kind of cut through with this plane z equal to 1. And this is a sphere of radius 2. Okay. And the density function is given. So the only difference between the examples we have done so far and this is that we're finding the mass here, not the volume. Okay. The density is given as z over x squared plus y squared plus z squared to the power of 3/2. Okay. The question is again to find, no, not again. So the question is to find the mass. Okay. So mass is the triple integral of the density over this solid T. Once again, the question is, which coordinate system is better here, cylindrical or spherical coordinates? Spherical coordinates because okay, so spherical coordinates, which is the upper bound. Okay, that's good. What about this one, the z equal to 1? This is going to create some problems. Okay, so spherical coordinates is probably what my first thought would be, but the z equal to 1, remember, is probably the flattest thing you can think about. Okay. If there is anything where you cannot use spherical coordinates as the first choice, z equal to 1 is right there. Okay, so this is your center and draw your axis. Z equal to 1 is kind of elevate. If it was sitting on the xy plane, I wouldn't have thought about it twice. Okay. Yep.
So because z equals 1, it's not just like the equator of the sphere. Does that mean that we just have to like find the corresponding row?
Yeah, it makes problem. Yes. So now the problem is a little bit tricky, right? Because it's not sitting on the equator. We have to be careful. But the biggest hint that you should use spherical coordinates here for is something else. What is that? This thing here. Okay. You see this, don't think twice. Use spherical coordinates. Whenever you see x squared plus y squared plus z squared, that is a 100% guaranteed thing that you can do. Okay. Use spherical coordinates immediately. Don't think twice. We will deal with other things as it comes. It's still not the easiest way to do it, okay? But using cylindrical coordinates is a bad idea. Yep.
Would it make our lives easier if instead of like stuff with the normal row and all that, we just plug in 4 for x squared plus y?
No, because then you're assuming that the density is constant. You cannot plug in anything there. You have to integrate through the whole solid. Okay. So this is what I would write. Note. If the question was to find the volume, not the mass. Okay. I would have surely gone for cylindrical coordinates. Reason is because in cylindrical coordinates z is just 1, okay, and this one you can write as z equal to square root of 4 minus x square minus y square, which you can write as the square root of 4 minus r square. Okay, that's a lot more easier to manipulate in cylindrical coordinates if the question was to find just the volume. Okay. Here, unfortunately, we have this density term which has x square plus y square plus z square. That is why we are left with no choice than use spherical coordinates. It's all about what is given, what you're trying to do. Okay, don't just be with prejudiced about doing something and you are going to make it work. That's not going to happen. Okay. So we have to convert this in terms of spherical coordinates. So delta of rho theta phi. Z is rho cosine phi. Now you have to convert everything, right? You cannot have any more x, y, z or r or anything. You have to convert everything in terms of rho theta phi. And this is just rho squared to the power of 3/2. You don't have to again plug in all that stuff there and start simplifying things. X square plus y square plus z square is rho square. So this is rho cosine phi divided by rho square to the power of 3/2, which is rho to the power of 3. And that's equal to cosine of phi over rho square. All right. So once again, the main problem here is that we are dealing with a flat plane and trying to use spherical coordinates. Okay. So the radius rho will go from this distance. Let's call this as rho min, and this is rho max. Rho is the distance from the center of the sphere to whatever thing you're trying to calculate. Okay. So your radius would be rho min less than or equal to rho less than or equal to rho max. Rho max is easy. That's sitting on the surface of the sphere. This is rho square equal to 4, so rho equal to 2. Okay. So you're going from the nearest thing to the farthest thing. To the farthest thing is on the sphere, that is 2. The nearest thing is what he was saying earlier. Okay. You're sitting on this flat plane. Remember that z is rho cosine phi. Z equal to 1 becomes rho cosine phi equal to 1. So you can write rho as 1 over cosine phi. You can write as secant of phi, but if that looks less appealing, you can write as 1 over cosine phi. So this is a small price here to pay for using spherical coordinates for a flat thing. Okay, that is not something that comes easily, because now your radius depends on your angle phi. Okay, for a good reason, because it's a flat thing. Because if you're here or here or here, the radius keeps changing. Okay. That's the tricky part of the question. So your radius goes from 1 over cosine phi to 2. What will be the limits of phi here? When do this, or when does this hemisphere intersect this plane? So when is z equal to 1? That means you have rho cosine phi equal to 1, right? So when this hemisphere intersects that plane, your rho is equal to 2, because the radius of the sphere is extreme at that point. Okay, this radius is 2 at this point. That is when those two things are going to touch each other. So rho is equal to 2 here. So 2 cosine phi equal to 1. So cosine of phi is 1/2. And that phi should be a familiar angle. What is that? Pi over 3, right? Because it's, so phi is pi over 3. Cosine of 60 degrees is pi over 3. And so it starts from the North Pole and hits that plane when the hemisphere is intersecting the plane. Okay, and that is when phi equal to pi over 3. That is the angle that is swept through. Yep. Because the hemisphere is intersecting this plane. The radius of the hemisphere is 2 at this point. They are touching each other at this time, right? We are trying to see when this thing intersects this plane. No, on the sphere, right? So this is a plane z equal to 1. At what point are we talking about the same thing for both? So the radius of the sphere should be equal to whatever distance you have traveled on this plane to that same point. Okay. So the hemisphere is going like this. It has got a fixed radius of 2. Okay. And it's intersecting this plane exactly at one point. Right. At that point, the radius of the sphere is still 2. And the equation of the plane is still z equal to 1. They are equal. Okay. So z equal to 1, rho equal to 2. So that will fix the limits for phi. So 0 less than or equal to phi less than or equal to pi over 3. Okay, so those are the limits for rho, which depends on the angle phi. Phi goes from 0 to pi over 3. What about the limits for angle theta? That's the least complicated thing. When these two things intersect, what is the shape that is created here? It's a circular disk. Okay, so the angle theta goes from 0 to what? Circular disk. 0 to, don't doubt that one. Circular disk 0 to what? 2 pi. Okay. You're not cutting this in the first octant or anything. Okay. That is the easiest part. So it's always 2 pi as long as you don't cut it out at any point. Okay. So the setup for the mass of the solid would be the triple integral. You should do the rho first, okay, because it's got phi in it. 1 over cosine phi 2. And phi goes from 0 to pi over 3. Theta goes from 0 to 2 pi. Density function is cosine of phi over rho square times rho square sine phi d rho d phi d theta. The problem is so well set up that once you plug in those limits there, the integral becomes so easy. Okay. So the struggle is all with this part here to set up the right limits, especially for rho and phi. Once you do that, it becomes a pretty straightforward thing. So on the test, what I do is I just mix up these things. I'll take bits and pieces of one problem and put it in the other one. So make sure that you're familiar with all these things. Okay, like the density term in this one, you could expect that in an ice cream problem. Okay, so that's how you kind of create different questions in calculus 3. So just have a clear idea in mind what coordinates to use where. Okay. So typically cylindrical coordinates for paraboloids, cylinders. Okay. Even if there is a cone inside the cylinder, you could still use cylindrical coordinates because it's not a difficult thing to manipulate a cone. Okay. Spherical coordinates for spheres and cones. And in all these cases, pay attention to anything that involves mass or something. Okay. If the density has a term that is looking easier in terms of one or the other, always go for that one. Okay. So look at the density term. If it looks like x squared plus y squared, go for cylindrical. X squared plus y squared plus z squared, go for spherical. This is where practice comes in. You look, see a few of these questions one after the other, kind of get an idea about which to use where. Okay. The last thing to do is to start with the wrong coordinate system and waste a lot of time trying to figure it out. So just have a clear idea in your mind where to start and just go with that. Okay. So do this problem assuming that we did not look at it. Just do it yourself, see if you can set up the limits and then do the integral. And just put yourself in the position of those students who wrote the final exam in 2017 fall and see if you could have done it. Okay? Some of them did it, some of them got the limits wrong, but the important thing is to at least attempt it. Okay? Don't just flee from the question without doing anything. All right, so that is the end of 3.6 and 3.8. So anytime that we have remaining tomorrow, I'll make use of for doing any of the questions you want me to go over. So please do the homework, all the old exam questions and everything. Okay, so make sure that all of you are comfortable with all these calculations. All right, then let's do something which is going to be a little bit different now. Okay. Before I do that, do you have any questions about any of these? Yeah.
Another question about like
Mm-hmm.
roving two, the circle is smaller. Plus equals one, like higher end. Since we're measuring.
No, that's why we are integrating the inner one, right? When you're sweeping this through, we are not assuming that rho is fixed. So this part here depends on the position of where you are. But what you're asking is correct, that rho is not fixed. That is what this part is doing. You're kind of going through that part. And once you fix that one, you go into the next one.
So what is rho equal to?
On the surface. So the equation of the spherical region is given by this: x square plus y square plus z square less than or equal to 4. This is talking about the surface and inside the sphere. Okay. So what I'm talking about there is you're walking on the sphere and hitting this flat plane.
Yeah.
That is the point where they are exactly equal. Right? Everything else you are kind of in control of this term because you're changing with the position of where you are.
So are we breaking the radius from z equals one?
Yes. You're measuring the radius always from the origin because that's how we've defined your rho. Okay. So the radius is always measured from the center to this point and to that point.
They're the same.
No, this point is given by whatever position you are in. Okay. And on the surface, the radius is the same. So you're going from the surface to the surface of the sphere. On the surface, the radius keeps changing because it's a flat thing. From there to the surface of the sphere, that is how your rho is changing. And once you do that, you can assume that rho is equal to 2 on the surface of the sphere. Okay, this part here. That is what takes care of the intersection of the two. We've done that for all the problems. You know, the second part is where you kind of crush it into the next plane. Right? That's what it's doing. All right. Any other questions you want me to clear up on this? This has always been a contentious problem, believe me. So it's not the first time this problem is, and that's one of the reasons why I do it in class instead of leaving it as an exercise. All right. Now to some slightly different notations and concepts. Okay. And to make sure that you don't go insane with what we are doing, just pay attention to what we do in class and stick to the kind of examples we do. Okay, don't go and do all kinds of crazy things. So the concepts we need from chapter 1 are the following. We're going to do sections 2.8 and 3.11 simultaneously. Okay. And there's a reason why these are covered at the same time. So the concepts we need from section 1.5. That's when we first talked about, and probably the last time, we talked about the cross product of two vectors. We have two vectors, u and v, with an angle theta between those two. The area of this parallelogram is given by the magnitude of U cross V. That's something we have seen, I don't know, 4 weeks ago. So since it's summer, I can kind of look back quickly instead of a regular semester. Okay. So U cross V is a vector that is perpendicular to this plane. And the magnitude gives you the area of the parallelogram which is spanned by those two vectors. What if you remember this? Or kind of. And to calculate this, if you have U equal to U1, U2, U3, and V equal to V1, V2, V3, U cross V used to be this 3 by 3 determinant. We have reached a stage where we're going to make use of all these things in one place. Okay. This is where math can look a little bit crazy, at the same time, kind of very impressive about how to collect all these seemingly different concepts. So that is one part of what we have seen. In chapter 2, we looked at surfaces of this form, z equal to f of x, y. It's got 3 variables in it. Okay, so there are 2 independent variables, 1 dependent variable. That is what creates a surface in R3. So for example, this is a surface, okay, z equal to x square plus y square. Your surface of the sphere is another surface, okay, not the inside of the sphere, the surface of the sphere. Or a cone is another surface. The cylinder is also another surface, if it's probably more familiar to you. The question is, how do we find the surface area of these surfaces? Okay. How do we find the surface area? All of you know the surface area for a cylinder. It's the circumference times height. Circumference is 2 pi r, height is h, 2 pi r h. You have done that in your high school. Okay. How do we get the surface area for a regular surface like this? If there are no holes or gaps or anything in between, if it's a nice smooth surface that you can walk around, okay, how do you find the surface area? Remember that areas are related to double integrals. Okay, so we are going to find the double integral of something, and the question is what that something is. We need to create something easy so that we can make use of this part here. Okay, remember this is area. Okay, so we have to make use of that concept and somehow make use of the surface part here, use that thing into here and see what happens if you combine the two. Okay. So the question is, can we use the cross product idea for surfaces of the form z equal to f of x, y? The answer is yes, you have to make some small adjustments. Okay. We can do what we call as the parametric form for a surface. That might sound like a very heavy topic to think about. Okay, the idea is pretty simple. If you look back to your case in calculus 1, so y equal to x square, you can define x equal to t and y equal to t square. The t is called a parameter. So if you give a value for t, that defines both x and y. You have seen this even for straight lines. So it's a parametric form for straight lines in chapter 1, right? T was a parameter. Similarly, if you have x square plus y square equal to, say, 4, you can write x equal to 4 cosine t, y equal to 4 sine t. The t is a parameter. In this case, t goes from 0 to 2 pi. In that case, there is no limit on t. You can give t equal to positive or negative numbers. So for a curve in R2, we needed just one parameter. For curves in R2. So you have two variables, one parameter. Okay, that is the pattern I want you to develop here. Two variables, one parameter. Now you've got three variables. How many parameters do you think we would need? If two required one, three requires two. Okay. So we need two parameters. We will name these parameters as u and v. The parametric form, as weird it sounds, it's just an alternate way of writing the same surface. So for example, if you have z equal to x square plus y square, you can write x equal to u, y equal to v, z equal to u square plus v square. That is what I mean by writing a surface of three variables in two parameters, because z connects x and y. Okay, so you don't need a third parameter here. Using these two, you can create a third one. So any point on the surface can be written by this vector r of uv equal to u v u square plus v square. Okay, that's your x, y, z. Okay. So the first thing you need to make sure is that you don't get scared by seeing the parametric form. Okay, it's just using two letters instead of three and making a connection between those letters. X equal to u, y equal to v, z equal to this. But there are many different ways you can do this, right? If you can write x equal to square root of u, y equal to square root of v, you could write z equal to u plus v. Okay. Then you have to make sure that u and v are positive. Okay. So many different parametric forms are possible for the same surface. And all of them are correct as long as you don't violate any of the points on the surface. Okay. All the points on the surface should be defined exactly how it is in terms of x, y, and z. So if you just write u, v, u square plus v square, that is going to just sit in place of x, y, and z. Okay. All right, so in general, we can parameterize in a surface z equal to f of xy as r of uv. It's written as a vector because it's got this x, y, and z components, which represents all the points on the surface. Okay. As u, v, f of uv. So x, y, and z. The key thing is that you don't need a third parameter. The two parameters takes care of the entire surface. Or other acceptable forms. This is the safest way you can do this. Okay. What do you mean by other acceptable forms? So Another way of writing the same thing, z equal to x square plus y square, is you can write x equal to u cosine v, y equal to u sine v, and z equal to u square cosine square v plus u square sine square v. Okay, that is your x square plus y square. And that's equal to u square times cosine square plus sine square is 1. Okay. So that is another way of writing the same surface. So in this case, it will look like this: u cosine v, u sine v, u square. Okay. Both these things are representing the same surface. They look different. Okay. But depending on how you define your u and v, okay, both this form I written up here and this form are both correct, and both represents the same surface, z equal to x square plus y square. Both are correct and both are useful. There's nothing called which is more correct. Okay. It's all about which one is easier for you to come up with. So if you were doing this for the first time, which one is more natural to you, the first one or the second one? First one. Okay. So it's all about that. I mean, the second one requires a little bit more craftiness to think about cosine and sine. The first one is more automatic. Just set x equal to u, y equal to v, deal with z. Okay. So can you write the parametric forms for the following surfaces? Again, many answers are possible. Okay, so first one, x square equal to y plus z to the 3, 2, x equal to the square root of y square plus z square, and 3, z equal to 2x plus 3y. The last one is a plane. Okay. Can somebody online give me a suggestion for the first one? Again, you can do it in different ways. So there is no correct or wrong answer here unless you're doing something ultra crazy. Okay. So can you suggest something for number one? And it's okay to be not correct. Nobody's going to judge you. X equal to u, y equal to v, good. So if you do that, okay, x equal to u, y equal to v, then you have to first write the equation as z to the 3 equal to x square minus y, and write z as the cube root of x square minus y. I have no problem with it. Okay, so if you want to do it, you can do it as x equal to u, y equal to v, and z would be the cube root of u square minus v. Is there an easier way to do it? Here's a hint. Okay, you don't have to put x equal to u always first. You can start with any of those things as the first letter. So can you try it now? This is what I would have done. Okay. y equal to u, z equal to v, then you have x square equal to u plus v to the 3, or x equal to plus or minus the square root of u plus v to the 3. That is also possible. So that's what I said. There is no the correct answer. Okay. All of you okay with this? What about the second one? I think that should be more straightforward. Second one, any answers here?
X equals U, plus minus square root of
Okay, so one of the answers is x equal to u. The only problem with this is the manipulation of terms, but it's okay. Y equal to v and z equal to plus or minus, what did you say? Okay. What is a more straightforward way of, yeah? Yeah. That is a little less tedious. Okay. That we don't have to deal with the plus or minus dilemma. Okay, so just put y equal to u, z equal to v. So I got two of the parameters representing that whole surface, which is actually a paraboloid which is sitting along the x-axis. Okay. What about the last one? That's easy. Y equal to v. What is z? 2u plus 3v. So once again, when you write this, you can write it as a vector with these as the components x, y, and z. Okay. All right, so remember we are trying to find the surface area. Okay. So taking a surface, z equal to f of x, y, which is now represented in a parametric form as r of uv. Now that you're kind of familiar with what I'm trying to do here, I've gone from the xy world to a uv world. And let's take the surface to be something like this. Some surface in terms of x and y, which is now in terms of u and v. Let's create some grids along the u and the v axis. This is your r of uv. And let's fix this as your u axis and this as your v axis. Here is one of the facts from your calculus 1. Okay, the derivative is always tangential to the curve in calculus 1, or here the partial derivative is going to be tangential to the surface at that particular point. Okay. So if you take any particular point here, the partial derivative of r with respect to u will be tangential to the surface at that point. This is r partial u. Partial derivative of r with respect to WRT means with respect to u. And similarly, along the v-axis, the partial derivative of r with respect to v would be tangential to the surface in that direction. But these are along the axis. Okay. Along the u-axis, they have partial r with respect to u, and along the v-axis, they have partial r with respect to v. Based on something I mentioned maybe 5-10 minutes ago, what is the meaning of the vector r partial u cross r partial v? It represents a vector which is perpendicular to the surface. Okay. It's a normal vector, to be more precise. Okay. So vector perpendicular to the surface at each point. This vector should not be equal to 0, because if it is, then the surface is not meaningful. Okay. So this should not be equal to 0 at any point. Because if it is equal to 0, that means there is no normal vector. That means we are kind of standing on a surface which has no orientation. If it is not equal to 0, we say that the surface is locally regular. It's just a fancy way of saying it's continuous. Okay, there is no gap or hole anywhere on the surface. Surface is locally regular if and only if the cross product of the partial derivatives is not equal to the 0 vector at that particular point. So again, this means that the surface is smooth, or there are no holes or gaps or no sharp corners or anything. Those vectors are very useful. Okay, so this entire 2.8 and 3.11 are based on just those two vectors. So if you make use of them cleverly, it's a very easy set of things to deal with. Okay. So concept number 1. Any vector on the surface, which is any tangent vector on the surface, is created by a combination of RU and RV. RU means R partial U. Okay. So if you look at those two vectors, and if you just combine all of them together, that creates the entire tangent plane to the surface. Okay. So we can write the equation of the tangent plane in a slightly different form, in the parametric form. Assuming that it's locally regular, that means the cross product should not be equal to 0. Okay. At any point P, as x, y, z, that is the x, y, and the z coordinates of the tangent plane, equal to x naught, y naught, z naught. That is the point P. Plus some parameter a times r partial u plus some parameter b times r partial b. So all you're doing is, instead of going back to the original surface in terms of x, y, and z, you can just use the parametric form to just write a tangential plane. Okay. And that will give the same answer, because all those vectors are just covering up the whole surface. So you are generating the entire combination. This a and b are parameters. That is what you would have done in section 2.8. Now we are doing both at the same time. So, okay, entire section 2.8 is dealing with writing the tangent plane to a surface in parametric form. Okay, that is what it is. The more important concept is this. This is the main part of section 3.11. Okay, so pay attention to this. You're trying to find the surface area of this part here. Now, if you look at any one particular shaded part of this, that looks like a parallelogram. Okay. So to find the surface area, this parametric surface, just take one of those small parallelograms. You know the sides, this is RU and this is RV. The area of the parallelogram from chapter 1 is the magnitude of RU cross RV. That's why I wrote that earlier. From section 1.5, you know that if you know the vectors which give you the two sides of the parallelogram, okay, the area of the parallelogram is the magnitude of the cross product. So what do you do to get the area of the entire surface? Add up all the parallelograms which are sitting all over the place. So the total area would be a double integral over the entire surface. So one of the integrals will be for u, the other one will be for v. Okay. So double integral of this of the magnitude of Ru cross Rv du dv. So that is a lot of things going on in there. Okay. So you got vectors, you got cross product, the magnitude of vectors. In a way, it's a summary of what we have done this semester. Partial derivatives, then you're doing double integrals. Yep.
So is it just taking the constant?
It's not a constant, you will have u and v terms inside it. So depending on the surface, there will be some u and v terms. We are not doing it at a point. Yeah, those are partial derivatives. So there will be some u, v functions there, which we hope will be nice. Okay. Take its magnitude, integrate it. So that is the golden thing from section 3.11. So it's probably one of the most cumulative formulas that you have seen in your life. Okay. It's got a lot of things that you have seen. It's got partial derivatives, then there's a cross product of vectors, double integrals, so all kinds of things. Yep.
So just to clarify, when you're taking the magnitude of that cross product, is that a constant or is that still a function of u?
That's still a function of u and v.
Okay.
Yep. You're not doing it at any particular point, you're doing it for the entire surface. So there is a u range and there is a v range.
Also, why do you do the cross product of the partial derivatives, not just of the u and v vectors?
Well, because we need the surface parametric form. This has to picture into your calculation in some form, right? You're finding the area of the surface, not of the grid.
Okay, so u and v aren't just like set vectors, we have to find the partial derivatives. Right?
Yes, so take the parametric form, find the partial derivatives, find the cross product. Okay. So let's get used to this process. So it's not as bad as it looks. I know the notations look crazy, okay. But once you start doing it, you know, you'll get pretty accustomed to it, and shouldn't be too hard. So what we'll do today is to get done with the first two problems of worksheet number 11, where we're going to do just the locally irregular part and the tangent plane, and we'll do the surface area part tomorrow. Okay. That way it won't be too heavy. So worksheet 11, that's the last worksheet for this test. Okay. All right. Unfortunately, this will come back in chapter 4 again. That's one of the reasons why it's done as late as possible. Okay. Please don't forget this total area thing that I wrote there. Okay, so problem 1 in worksheet number 11. You're given the parametric form. That's always given to you. Okay, so you don't have to scratch your head and try to figure out the best parametric form and so on. R of u v equal to u minus v, u plus v, and u square minus v square over 2. As soon as you see this, you should understand that these are the x, y, and the z coordinates. Okay, those are the things you need to understand here. No matter how complicated those UV things look like, ultimately those are the x, y, and z coordinates of each point on the surface. Okay. And you're also given a point P on the surface given by 4, 2. Those clearly stands for the u and the v coordinates. If there are 2 of those are the parameters, 3 of those are the coordinates. Okay. So this corresponds to x naught, y naught, z naught equal to u minus v, which is 4 minus 2, okay. U plus v, which is 4 plus 2, and u square minus v square over 2, which is 16 minus 4, 12 over 2, 6. Okay, so this is u minus v, this is u plus v, this is u square minus v square over 2. That is the corresponding thing. The point in terms of the parameters, the point in terms of the raw coordinates x, y, z. So the first question, can you write that surface in terms of x, y, and z? Just using simple algebra. Can somebody tell me what that is? You cannot see the Zoom crowd. Let me see if they have an answer. So some kind of an algebraic connection between the x, y, and z parts of that function.
Is it 1
Hint.
half x times y?
Z equal to x times y, is that?
1 half x times y.
Okay, so z equal to 1 half x times y. All of you agree? Good. A minus b times a plus b. Your kindergarten teacher told you it's a square minus b square. Okay. So z equal to 1 half x y. That is what is connected here, x, y, and z. Okay. So that question is to make sure that this is nothing alien. This is the same stuff written in 2 different ways. Good. Yep, that's right. Part B. Prove that the surface is locally irregular, and that's where we had to find. So locally irregular means that the normal vector is properly defined. Okay, that this is not equal to 0 at this point. Okay. It could be 0 somewhere else, I don't care. But right now, we just focused on that particular point, and you have to prove that this is not equal to the 0 vector. Okay. How do you find the partial derivatives? I hope you remember this. Okay. Partial of r with respect to u. Take each component and find its partial derivative. The partial derivative of u is 1. The partial derivative of the second component is also 1. Okay. Because you have u minus v, that will be 1. This will be 0. You remember that, or it used to be a long time ago, right? Partial derivatives. What about the last term? What is the partial derivative of the last component? U. If you want, you can plug in the point, which is 4 for u. Okay. 1, 1, 4. Since we are focusing on that one particular point, you can just plug it in immediately. And partial r with respect to v would be. Can somebody online tell me what the components would be? Could be an embarrassing question, but.
-1, 1, and negative v.
Negative v, good. And when you plug in v equal to 2, you get -1, 1, -2. The question is, are these two vectors parallel? Okay, when you say that the cross product is not equal to 0, they are not parallel vectors. So they don't look parallel to me. One is not a multiple of the other, but finding the cross product would kind of double confirm that fact. Oops. So RU cross RV is, again, it doesn't matter whether you do RV cross RU or RU cross RV. Okay. IJK 1, 1, 4, negative 1, 1, negative 2. We forgot how to do a determinant. Don't forget the positive, negative, positive sign convention. Okay. What we want to see is, are we going to get all the components equal to 0? I think as soon as you do the first term, you get the answer, right? That's negative 2 minus 4, negative 6, already not equal to 0. So just complete it. That's going to be negative of negative 2 minus negative 4. That's negative 2. And k times, what is here? 1 minus negative 1, 2. I hope all of you remember how to do this. So this multiplied minus that multiplied, okay, that's negative 6. You have to cross out the middle column and the first row. 1 times negative 2 minus 1 times 4. Okay. Did I miss up a sign? Which one? The second one? That's a negative of negative 2 minus negative 4. What am I missing? It's okay, right? Yeah, that's a misleading term. Either way, it's not equal to 0. That's all we need. So that is what means by saying it's a locally regular surface. Which means that the surface is well defined at that point. There is no gap or sharp corner there. Okay. If that's the case, you could define the, is that a part C? Forgot. Write the tangent plane to the surface in the parametric form. Okay. You already have all the ingredients you need. So the tangent plane in parametric form is, don't forget the left hand side, xyz. Okay, that defines each point on the tangent plane xyz equal to x naught, y naught, z naught, which is the point 266 plus some parameter. Okay, that's why it's called the parametric form. Okay. Some parameter a times the first partial derivative 114. So all it says is that, taking any combination of these vectors will create a tangent plane. Okay. Plus b times negative 1, 1, 2. So once you have everything calculated, it's just a question of putting them in the right place, and that's it. There is no need to simplify it further. That is the official way of writing a tangent plane in the parametric form. Yep. That will pass through the point, which point? A, B are parameters. So what this says is that this is true for all values of A and B. Yep. So that includes, x, y is equal to 266, but you could give A equal to 1, B equal to 1. A, yep. So A and B are parameters. So in fact, if you separate out the x, y, and the z components and simplify it together, you will get the tangent plane like you did in section 2.7 for that. That takes some time to manipulate it, but you will get the same answer either way. All right. Any questions about that one? Let me go back to my Zoom people. Any questions about this? All right, now the second one, which is on similar lines, except that I have a lopsided parenthesis created there, but except for that, same idea. Did all of you write this? I'm erasing the wrong board. Okay. So can it says sketch the surface in a kind of a light way. You don't have to be artistic about it. Can you tell me what kind of surface this is in the XYZ without making it too complicated? What is the equation of the surface?
X equals y squared plus z squared.
Good. So it's x equal to y square plus z square, and that is what? If you draw the surface, it's a paraboloid sitting along which axis? X-axis. So that is what I mean by sketch the surface. So when you see it, it looks scary. Oh my goodness, what is that? But once you put it in terms of X, Y, Z, okay, not too bad. Well, let's see. So the partial derivatives are nothing fancy. Oh, at the point 1, 2. And don't forget that this corresponds to x naught, y naught, z naught. Equal to 5, 1, 2. Okay. That's u square plus v square uv. I write 512 now and then, 5 minutes later, look at it. How did I get that 512? That's why I just write that below it. You'll go crazy later if you try to make sense out of notes. All right, let's do your RU cross RV and make sure that it's not equal to 0. So I'm doing this even if I know that it's not equal to 0. So good practice for the surface area problems, but you really have to do it. Okay. Since it's I times 1 minus j times 2 . So what I get? So at that point, RE cross RV is a vector 1, -2, negative. Please don't add those things. Okay, it's a vector. So please leave it. That's not equal to 0. So it's locally irregular. So in a parametric form, you can represent the tangent plane to that surface at that point. At the point phi 1, 2 as xyz equal to phi 1, 2 plus some parameter a times the first partial derivative, which is 2, 1, 0, plus b times 4, 0, 1. So any vector that originates at this point and goes towards those two in any combination will generate entire tangent plane. All right, I think that will be a good place to. Isn't the last value 0, is it? This is 0 minus 4, that's -4. I hope, yeah, you multiply with k, okay, please don't multiply it with 0. It's k times this. So you can now do most of the old exam questions and everything, okay. Let me just tell you what the pattern of test number 2 would be, just so that you know how to plan for it, okay. I'm just trying to ask 5 questions. Reversing the order of integration. It's a double integral. Polar coordinates. Again, please do all the examples we did in class and the old exam questions. Okay. 1 spherical coordinates. 1 cylindrical coordinates. And 1 surface area question, which we will cover tomorrow. Okay. But we have covered the concept today, so you're taking the cross product and kind of taking the magnitude. So those are the 5 types of questions I'm covering on test number 2. So you should be able to do most of it at this point, except for number 5. All right, I have office hours at 12:10. If you have any questions or bring any other questions to lecture tomorrow, we can go over it. I don't plan to start chapter 4. So after we are done with this, we can discuss anything. All right, then, that's it. Thank you.
Will you tell us to use Spherical?
No, that's the part you have to, but I think I gave you enough hints today, so it should be pretty obvious as to which one.